So if you see the syllabus, you will see that it starts with these two words, quantum postulates. Quantum postulates, the topics under this title, whatever the topics they are, I suppose that most of you or almost all of you know what are those topics. Maybe not in depth, but definitely have come across the concepts under quantum postulates. Why this is so, why I'm saying that some of you or most of you, because in some textbooks they separately mention those concepts under the heading quantum postulates, like Peter Atkins, McQuarrie Simon, Engel and Reid. They have separately mentioned that what do they mean by quantum postulates. They were formed in 1930s actually, but the concepts were already there before 1930. So in some textbooks they have discussed the same set of concepts, but without mentioning that they are called quantum postulates. So that's why, say for example, Levine, there is no mention of quantum postulates, right? And in many other books they have not mentioned. So that's why I'm saying that some of you might have known it, the name quantum postulates, and some others have not. But the concepts, of course, everyone you know. So that's why probably it is included in the PG syllabus in the very beginning, that to have an outline or review of the quantum postulates as such. Okay, so that is our topic, quantum postulates. The next, some pages would be there, handwritten, written by me. So let me start like that. That quantum postulates, actually you know already, some of the concepts are introduced in your earlier BSc courses, quantum concepts. So in a single sentence, what do you mean by quantum concepts? There are some concepts which are of course very new, some revolutionary, some new concepts, and more importantly, those concepts, they don't have any classical analog, right? So in classical mechanics there is no such things. That's why they are very new. For example, let me state 4 of such. Wave particle duality, it's something new. Quantization concept, uncertainty principle or uncertainty concepts, and probabilistic nature of some law. So these are, to say a few, which are very new and we can call they are quantum concepts. Since then we know that particle, say for example electron, it has some wave character. So that we know now. Now if a particle is associated with some wave character, then to explain it on script, to explain or to narrate it, to understand it, to manipulate it, to use it, you need some wave function, simply wave function, say let us call it psi, and of course it would be a function of position and time, because the particle is somewhere at some time, so the variables are going to be of course the position x, y, z, and of course time t. So psi is in general a function of x and t. Well, that is the wave function. Because it's a wave, so there is a wave function. But at the same time, particle has many properties, right? Property by property we mean that it is something measurable, it is something observable, you can measure by some instrument. So the particles have some properties, and how we can measure in quantum mechanics those properties, right? We can have finally some numerical value as the measured value of those properties, first of all, and secondly, how those properties that we can obtain from the wave function associated with that particle. So that means how property and wave function, psi and the property, how they are connected, interrelated. Sometimes we call the wave function as state function. So to bridge the link between this property at one hand and wave function on the other hand, this bridge between these two, we need to introduce something, and they are, as you know, they are operators. we call it A cap or A hat, capital A. And the second thing we need, that is EVEF, eigenvalue eigenfunction equation, and it looks like that A psi equals to A psi. Right hand A is small, which is a numerical value that represents the measured value of the property for which A cap stands for as the operator, right? So this is the eigenvalue eigenfunction equation. So these are the things I am just reviewing that we already know, irrespective of whether you know about postulates or not. Okay, for example, A psi equal to A psi, small a psi, the most prominent example is the Schrodinger equation itself, right? H psi equal to E psi. So here H cap or H hat is the A hat. So it's an operator and psi is the wave function. This E is the eigenvalue and psi is the wave function. So this is the special kind of equation, we call it eigenvalue eigenfunction equation, where H cap is called the Hamiltonian, and it consists of the two operators, kinetic energy operator P cap and potential energy operator V cap, right? And that also we know that the total form of H, because we know the operator form of T hat, you know the operator form of V hat. So overall H hat is something like this. For three-dimensional or three-dimensional system, lambda square is simply called Laplacian or the del squared, and which is nothing but del 2 del x2 plus del 2 del y2 plus del 2 del z2. How they come, that we know actually. I am not discussing all the preliminary details, but this is all about the energy eigenvalue, right? Energy value. So the question now, what about other value? That means values of other observable. Energy is not the only observable, right? Suppose some A is there, some other observable, capital A. So its corresponding operator is A hat, and this is representing the average value of property A when the system is in state psi. So that is something like this. That also you know how to evaluate the average quantity. So next question may be that okay, I have got a lot about psi and its use, but what really it physically means, psi mane ki? So this is the question, and if this is the Schrodinger equation, then how come Schrodinger equation? And if this looks like the eigenvalue eigenfunction equation, then why this equation is like that? कहाँ से आया एरकम देखते क्या? And moreover, why H cap looks like this? So the outcome that everyone knows, but probably have not asked the in-depth questions, that this how, why, and when. And finally, if psi is the wave function, how it is significant, and the way it is significant, why so, right? So I am trying to answer a few why and how on something that you already know, right? In fact, the answers also you know, but I am just trying to systematically summarize it. So in fact, all those answers are actually given as 6 postulates. So that is the introduction, that what are postulates and why we do need postulates. So the questions I raised actually all are answered by in terms of 6 postulates. So a few more points about the postulates. Number 1, they give a convenient framework of the foundation or basics of quantum concepts. Number 2, all of these 6 postulates are tested experimentally and extensively, and outcome are not in conflict with any experimental results. They give a set of rules of how information is obtained from psi. So psi is a necessity because we are calling particle wave, so there must be a psi. But well, after getting psi, how it gives the other property? What are the rules? And after getting psi, then another question: how do we get that psi? Right? Okay, we get it from Schrodinger equation. Then the next question: where from Schrodinger equation comes? Okay, it involves some Hamiltonian. Then the next question: how Hamiltonian is formed? So there are many questions are there, and we'll get the answers from these postulates. What we have studied so far irrespective of whether you have used the term postulates or not, but in the earlier courses, BSc courses, what we have done so far is actually that we have applied those postulates knowingly or unknowingly to some model systems and compared to the results from classical mechanics. So that means we have tried to explore that quantum world, quantum results, new results, which have don't have any classical analog. So we just tried to test those results in comparison to the classical results by applying some quantum rules on some model system. But those quantum rules and strategies we have applied, actually we have applied unknowingly the quantum postulates. So our today's motto is, we will see the postulates, explain what do they mean and how it may be applied further. Okay, so is it okay with you so far?
Yes, sir.
Okay, then I will request one of you, any one of you, please read out this paragraph.
Quantum mechanics can be formulated in terms of 6 postulates. A postulate is a claim or an assumption of truth, especially as a basis for reasoning. Postulates can't be proven, but they can be tested. The 5 postulates discussed in this chapter provide a framework for summarizing the basic concepts of quantum mechanics. The quantum mechanical postulates have been extensively tested since they were proposed in the early 1930s. No case has been found in which they predict an outcome that conflicts with the results of an experiment. The 6th postulate will be introduced in chapter 10.
Thank you. So what I'd like to pick up 2 words, that what postulate, by dictionary, what postulate means. Postulate is something that it's a proposal kind of thing, it's an assumptions kind of thing, assumption of some truth, but not verifiable by experiment, right? I mean, not of course it is verifiable by experiment, it is not provable in the usual sense. You cannot prove the postulate as we usually do in science, you know, starting from some basic principle, we derive, manipulate, go on mathematically, and finally reach at the truth. Okay, this is like that. At postulate you cannot do with postulate, right? You cannot do all these things, but you propose it on the basis of your reasoning, and then you can verify the outcome of that proposal or reasoning with the experimental results. So if it does match, then it's okay, and until that day or that moment it is okay, until we get some conflicting results with experiments, right? So fortunately till today all the postulates are standing still. We don't have any new findings, experimental findings, which contradict any of one of the postulates. So that is the meaning of dictionary meaning of postulates, and that's this one thing. Another thing is that it gives the whole foundation of quantum mechanics. So we actually will be discussing initially 5 postulates, and as it's mentioned here, it's taken from a book of McQuarrie-Sherman probably. In another chapter they have discussed the 6th postulate, but we will discuss at a stretch. Okay, so the next slide. Now let us start one by one the postulate. I have done wording in wordings of the postulates. There is a slight variation from book to book. Basically the thing is the same. So what I have done, I have collected the postulates side by side from 2 books. One is from McQuarrie-Sherman, another is from Engel and Reid. This colored one is from Engel and Reid, and the next one is from McQuarrie-Sherman. So let me read it out. Okay, one of you please read it out, the postulate.
Sir, আমি পড়ছি। Postulate 1. The state of a quantum mechanical particle is completely specified by a wave function psi xt. To simplify the notation, only one spatial coordinate is considered. The probability that the particle will be found at time t0 in a spatial interval of width dx centered at x0 is given by psi star x0 t0 psi x0 t0 dx.
Good. So this is the postulate. So at the first glance it doesn't seem much, but since you know a lot, actually it seems something to you. So let me just go through the other wordings. Someone else please read out this postulate taken from this is from Macquarie. Someone else please.
The state of a quantum mechanical system is completely specified by a function psi rt as a function of rt that depends on the coordinates of the particle and on time. This function, called the wave function or state function, has the important property that psi star rt psi rt dx dy dz is the probability that the particle lies in the volume element dx dy dz located at r at time t. If there is more than one particle, say 2, then we write psi star r1 r2 t psi r1 r2 t dx1 y1 dz1 dx2 dy2 dz2.
Thank you. Thank you very much. So you see, actually no difference is there in these two statements, but slightly presentation style is slightly different. First of all, in the first one it is referring psi xt, in the second one it is psi rt, and you know r is a coordinate, of course. In general it can be x or y or z, or both of x and y, or both of y and z, or all of x, y and z. That's just a general coordinate, right? The first one is talking about one dimension, and the second one is talking about the many dimension in general. So that is the only difference. Otherwise, the thing is that psi, it's called wave function or state function. State function because it explains the state of a particle. So it's a state function. That means it is in some way mathematically it's a description of a state of a particle, right? So how does it describe? What does it really describe? It is saying that if you take the product of this function, wave function, not really the product but psi star psi, or you can say mod psi square. So psi star psi, it is something, and when it is multiplied by the volume element, for one particle it is simply dx dy dz. You know, the volume element is given by that in Cartesian coordinate system. And for two particle, as he mentioned in the last line, and in general we call it actually d tau. So d tau represents the volume element in general. It may be dx simply in one dimension, it may be dx dy, it may be dx dy dz, or it may be r squared dr. Yes, r squared dr sin theta d theta d phi. So this is the volume element. So you just focus on the last line. It tells you the mod psi square or psi star psi into some volume element d tau. Okay, so the postulate proposes that psi is such a function, we call it wave function or state function, so that the mod psi square represents the probability density. Probability density. Now probability of what? Probability density is what? Density, you know, mass by volume kind of thing, right? Mass density is called mass by volume. So it can be a number density, that means number by volume. So if it is probability density, that means probability by volume. Okay. Now probability of what? Probability of finding a particle at a point, say r or x0, at a time t. So the probability, as I mentioned many times, that it is the probabilistic law. So it gives you the probability of finding the particle at a point at a time when you multiply the probability density, that is mod psi square, and the volume. As you get the mass as density into volume, so similarly probability is probability density into volume. So mod psi square is the probability density, and the volume element, when it's multiplied with mod psi square, it gives you the probability in a small volume. Okay, so get clear, probability density is something mod psi square, and probability in a small volume is density multiplied by that small volume, as mass is density into volume. Okay, clear? So this is from first postulate. Let me explain a little bit more. So explaining the postulates. P1, particle has wave character. Fine, I understand that. But in what sense a wave? Why it is wave? How? The better to start with, let us try to understand what we mean by wave in general, any kind of wave. By wave actually we mean a variation of something in that wave, variation of something regularly, and it's a kind of repetitive pattern. So there is a regular variation of something. If it is so, then we call it a wave. Say for example, in Digha or Puri or whatever wherever else, if you see the sea wave, it is a wave. Now, according to our definition or description, is it something variation of something? Yes, of course. A wave is nothing but the variation of water height in the sea content. In the variation, regular variation of the water height. It gives a pattern of height, and that we call a wave. So a wave, of course, is water, but the water is not wave, isn't it? But the wave is of course water, but not water as such. The regular pattern of water, that you are calling it a wave. Similarly, in sound wave, what is that? The regular variation is there of something. It is, the density of the medium, right? The contraction and expansion of the medium, that follow a regular variation. So again, by our description, it is a wave, sound wave. Well, in case of light wave, what is that something which is varying repetitively, making a pattern? It is the field, electromagnetic field. So you know that it is a regular variation of the electromagnetic field. So in a common sense, what we understand as wave, is it applicable for when I am talking about a particle wave? So the question in other words is that what is that in case of a particle wave? What is that? That follows a regular repetitive pattern variation. And if you get the answer, then you can satisfy yourself. Okay, I am convinced that why particle wave is called wave. The answer is, it is the probability density. So it's an abstract concept, it's not really physical something that you can play with on your hand. Like you cannot play with some wave on your hand. It is only in the sea. If you try to collect a wave, separate decouple a wave from the sea, then what you collect is simply water, not wave. So what is that? It is the probability density. So at different point, the probability density is different, and probably they follow a pattern, and that pattern is called particle wave. So now I think it is quite understandable or convincing that why a particle wave, in what sense a particle wave is a wave. Am I clear? Please, am I clear that what do you mean by
Yes,
particle wave? Okay. Now the next question. So if particle is a wave, and we now understand what we really mean by wave, and then the next question, that where from this description, mathematical description psi comes from? कहाँ से आ रहा है ये? The answer again, as it comes as a solution of Schrodinger equation, H psi equal to E psi. And one more thing, that whatever important psi is, psi itself has no physical meaning. So if you ask what does it mean, psi, my answer will be no meaning, very interestingly. But it is important. Then why it is important? Because, okay, psi itself may not have some physical meaning, but mod psi square has. It is meaningful. In what way meaningful? That I have already explained. It is the probability density, right? So psi square, mod psi square is probability density. That's why it is important, and that is measurable. That is, we can call an observable. Find the next question, that why it is mod psi square, sir? It could be simply psi square. Why it is psi star psi, not psi square? Why this peculiarity is introduced in this definition? Can you tell me, please? Can you have some light?
Psi star may have imaginary value.
Psi may have some imaginary value. Okay.
Psi.
So,
That's why psi star.
No, that's okay, but why? Even if it's imaginary, so what? Suppose psi is a complex function, maybe that we know that it happens, but then what the problem is? Problem kahan hai?
আপনি আগের দিন বলেছিলেন যে উইথাউট আই কোয়ান্টাম মেকানিক্স ইম্পসিবল, তো সেখান থেকে কিছু আসছে।
হ্যাঁ, সেখান থেকে কমপ্লেক্স হলো, ফাইন,
কেন হলো?
কিন্তু কমপ্লেক্স হলো তো হলো, তাতে আমি সাই স্কোয়ার নিলাম না কেন, মড সাই স্কোয়ার নিলাম কেন?
সাই স্কোয়ার কমপ্লেক্স মানে সাই মড সাই স্কোয়ার মানে হলো শুধু এর করছি আমি ম্যাগনিটিউডটার, মানে সাই স্টার সাই যদি নিই,
হ্যাঁ সেটাই মড সাই স্কোয়ার, সেটাই হলো, কিন্তু আমি সেটা নিচ্ছি কেন? আমি শুধু সাই স্কোয়ার নিতে পারতাম। ইফ দ্য স্কোয়ার ইজ ইম্পর্টেন্ট দেন আই কুড হ্যাভ
রিয়েল ভ্যালুটা আসবে।
হ্যাঁ
Sir.
হ্যাঁ, বল 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 বল, কে বলছিলি?
যিনি বলছিলেন
রিয়েল ভ্যালুটা আসবে সাই স্কোয়ার করলে, যেহেতু সাইজটা সাই নিচ্ছি।
সাইজটা সাই নিচ্ছি, তাহলে রিয়েল ভ্যালু আসবে। ইটস এ ম্যাথমেটিক্যাল ডিমান্ড that if you take the mod psi square, it would give you for sure a real value, and if you take psi square, simply psi square, and if it so happens that psi itself may be complex, then simply psi square may not be real. It may be, may not be, but mod psi square is definitely real. That is the mathematical something related to this concept. But the last part, okay, you are on the right track, but then why we are trying to ensure such? तो क्या साई स्কয়ার কমপ্লেক্স হতে পারে না হতে পারে, রিয়েল হতে পারে না হতে পারে, আর মড সাই স্কয়ার রিয়েল হবেই, এই অবধি ঠিক আছে, কিন্তু এটাই বা আমরা চাইছি কেন এত জোরের সাথে? এটা চাইছি বলেই
মানে আমরা যখন এমনি ভাবি তখন ইমাজিনারি সংখ্যাটা খুব অ্যাবস্ট্রাক্ট হয়ে দাঁড়ায়, সেজন্য।
ইমাজিনারি অ্যাবস্ট্রাক্ট হয়ে যাবে কেন? ইমাজিনারি ইজ ইমাজিনারি, ইমাজিনারি
রুট মাইনাস 1 তো,
হ্যাঁ, বাট ইন মেনি কেসেস দেয়ার আর ইমাজিনারি নাম্বার।
আচ্ছা স্যার।
হোয়াই
স্যার
বলো।
স্যার মানে ওটা যদি ইমাজিনারি বা কমপ্লেক্স হয়ে যায় তাহলে পার্টিকেলটাকে পাওয়ার প্রবাবিলিটিটাও তো মানে তখন কি করে পাবো সেটা?
Exactly, that is the point. You are on the right track step by step, right? You have answered properly, but not the wholly, step by step. The first point is that you have rightly told that sir, mod psi square is always real, because a plus ib is star is a minus ib. So if you multiply a plus ib into a minus ib, it would always give you a real quantity. But a plus ib whole square is not a real quantity. But the point is that if it is not real, then it's a problem, because after all, physically the postulate tells, here the postulate comes, the postulate tells that mod psi square is the probability density, and in our world of observation there is no such quantity, measurable quantity, observable, whose value is complex. Suppose if I ask Megha, how old are you? Then Megha is saying, sir, I am 17 plus 5i. It doesn't sense anything, you know. So any physical quantity, whenever we express in terms of numerical value, it is always real quantity. And here mod psi square has to be real, because it is corresponding to a measurable, observable quantity, probability density. So if a probability density happens to be complex, then it doesn't sense, it's as a measurable something. So that's why you have to ensure that it is a real quantity, and that's why you have defined not psi square but mod psi square. Clear?
হ্যালো স্যার।
হ্যাঁ বলো স্যার।
হ্যাঁ স্যার, বলছি কি যে আপনি তো বলেন এই সাইজটা মানে সাইজ মডেল স্কোয়ারটা আমরা মানে কমপ্লেক্সটা যাতে না অ্যাভয়েড করা যায় তাই জন্য এরকম করছি। তো স্যার বলছি সাইটাও তো মানে সাইয়ের রিয়েলের পাশাপাশি তো আমরা কমপ্লেক্স কনজুগেটটা নেব কেন? মানে আমরা নিই কেন কমপ্লেক্স কনজুগেটটা?
তাই তো বললাম যে কমপ্লেক্স কনজুগেট নিই এই কারণে, আদারওয়াইজ আমার the way I am defining, I am proposing, right, that some mod psi square as probability density, and since probability density has to be something real, so I have to define, it's for my convenience, otherwise it goes against my concept, and the postulate is proposing. So why the proposal should be in conflict with our experimental expectation? It should not be.
না স্যার, সাইয়ের ভ্যালুটা মানে সাইয়ের ভ্যালুটা আমরা মানে
সাইয়ের ভ্যালুটা আমরা
হ্যাঁ
নিচ্ছি না,
সাইয়ের ভ্যালুটা
সাইয়ের ভ্যালুটা আমরা নিচ্ছি না, সাই is coming as a solution of Schrodinger equation, so that is not under my control. It may come as a real function, it may come as a complex function. I am not quite sure because it is not under my control. It is coming from Schrodinger's equation. Now, after getting Schrodinger psi from Schrodinger equation, then I can play with it. I am defining something new quantity, and that is the postulate. The postulate is defining psi in such a way, I mean mod psi square in such a way that it represents the probability density. Now, is it clear?
Okay, sir. हाँ, sir.
Okay, thank you. Well, that is explained here that mod psi square is rho. This is rho. We call it probability density. And when the rho density is multiplied by some volume element, it gives you P, probability in the small volume dx. So rho is the density at xt and P is the probability around x in a small volume dx. And if you integrate over a range of x, say 0 to L, as in particle in a box, then this is the probability over a small volume rho dx, and now you are integrating over the whole volume or length. That gives you the total probability. So total probability, and total probability has to be, again mathematically it has to be always 1. Total probability 1 means the particle is somewhere there, of course somewhere there in that range. So that's why the total probability must be 1. And you know, in quantum mechanics, that we know as normalization, right? So we know the concept normalization and orthogonality, but that we know sometimes quite mathematically, and we don't bother to understand that why it is needed, the normalization, and how comes mathematically and more fundamentally. This is the answer, that more fundamentally the normalization is a necessity because of this fact, because the postulate 1 is telling you that this, right? So mod psi square has to be real. So if you just take the square of a complex quantity, then you may not get a real quantity cross, but if you take the conjugate and its original value and then take the product, then it must be real. You can check, you can do the product. This thing would give you always a real quantity where A and B are real, and the A plus IB as a whole is a complex quantity. Okay. So is it clear now? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir. Now, I am still in postulate 1. We are talking about a wave function psi, and now we are saying that that we have a civilized world. We have some rules, regulations in our society. So if someone new comes to our family or our society, then at least it has to follow some norms, some rules of our society. Now, so if you have a quantum society, so if something new is coming from Schrodinger equation after solving it for a particular system, and you are getting a psi, and now you are imposing that, okay Baba, you are a new person, you don't know the rules, but I am imposing, let me fix some quality on you, bacha tumi kintu egulo follow korbe, so that we can accept you as a bhadro shobho well behaved function. We can accept you, that's why sometimes we call it acceptable wave function. So that also the concept is very new or known to you from your graduation. I am calling it, it's my abbreviation, that you have to fix, you have to impose some quality. So you have to fix the fix, you have to fix the fix. It's like a rhyme, you can easily remember, that's why you have to fix the fix. So can you just try to explain this abbreviation? What does it FICS stand for? Just give a guess. I know you know, but still, just what are the meaning of FICS? Someone is joining. Let me. Yeah, someone is joining. Okay, let us try. That I have to fix some quality FICS on the function which is coming as an solution to the Schrodinger equation. So can I give you the full form? Can you give me the full form FICS?
Sir, F stands for finite.
Good. Go on.
And C for continuous.
Good. Go ahead.
S should be for square integrable.
That is I. Integrable. Integrable. That is I.
Oh, okay.
Okay. And S stands for? Anyone else?
Sir, single valued.
Good.
It's a single value.
Yes, right.
Yes.
Single value.
So as I started today's lecture, that whatever I'm going to talk on, you know a lot, and that you have proved that I was right. You really know a lot. Thank you. So FICS is finite, integrable, continuous, and single valued. And all the requirements FICS, that's well behaved requirement, they all are coming from postulate 1. Because the way it has defined mod psi square as the probability density, for that reason actually they are coming. Say for example, if somewhere the function is not finite at some finite point, then you cannot probably integrate the probability density multiplied by volume element. So it is not normalizable, right? You cannot do the integration. So finite has to be finite everywhere, otherwise you will not be able to integrate. On same argument, why it should be integrable? A function, you are getting a function, but it may be so that mathematically it is not integrable. Then you will not accept it, because it has to be integrable, otherwise how you can calculate the probability? And probability is something measurable that comes directly from psi, as postulate 1 is saying. So that would go against the postulate 1 if it is not integrable. And then why it should be continuous? By same argument, that if the psi square or mod psi square gives you the probability density, then at some point say the function is not continuous. That means the probability density is not continuous. That means the particle, you can talk about the particle is here, 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 and suddenly at some point you are not being able to say at that point what about the density. So the situation should not be like that. It's a common sense that it may be 0, but it must be continuous something, right? And similarly, single valued, if it is, say for example, if it is multiple valued psi, then mod psi square is again multiple at a given point at a given time. That means at a given point you are talking about 2 or more than 2 probability value. So how it is possible that you are here, the probability is 20%. At the same time I am saying you are here, the probability is 70%. How is it possible? It should be a single value, right? Because it is connected to the probability density or probability. So the postulate 1 actually is giving you the FICS. So you knew FICS, but probably you didn't know that it is all coming from a postulate, first postulate. And one more thing to note, that actually we can show that it's a mathematical requirement that the first derivative and the second derivative of function, wave function, they have to exist. Why I am not explaining, but supposing that the first derivative and second derivative, they have to exist, then it's a mathematical requirement that if the first derivative has to exist, then the function itself is continuous, must be continuous. And similarly, if the second derivative has to exist, then its earlier derivative, that is first derivative, have to be continuous. So that is the mathematical requirement for continuity purpose. And as I explained with the common sense, that it doesn't sense if I say that the function is discontinuous at some point. Okay. Well, this you just note. Okay, I will give you the PowerPoint file, so don't need it to write it down. But it's a problem, okay, for you. This problem is about normalization, as I explained what it is. It is nothing but integration psi star psi dx over whole range. Okay, the range is given here. For x it is 0 to a, and for y it is 0 to b. It's a 2-particle system, and the function is given like this. So you have to show that these wave functions are normalized. That means it's simply an integration problem. You just very easily you can do that. And this is actually a particle in 2-dimensional box problem, and it is done actually in McQuarrie's book. Okay, so if better do it on your own, and if you cannot, then you ask me, I will give you the solution page also. Another is about the acceptability. This is also from McQuarrie, and it's a very popular problem, frequently occurred in BSc quantum paper, that 4 functions, 5 functions are there, and you have to just mention, not derive completely. You have to mention that which one of these 5 are acceptable or not, on what ground. Okay, so the solution, the complete solution is given here, so you just consult it. Okay. Well, at one point I am going back to the postulate again, and I'd like to you see here it's completely specified, and the state of a quantum mechanical system is completely specified, and here again the state of a quantum mechanical particle is completely specified, right? So I am trying to give emphasis on this particular phrase, that complete description from psi. Why complete and how? So let me answer the first why. Why I am saying that once you get psi from Schrodinger equation, it gives you the complete description. So what does it mean? Why I am saying so? It is complete description in the sense that any measurable property or observable actually can be obtained using this psi. So that's why you are calling it, it gives a complete description. But the question remains that any measurable property can be obtained. Now the next question, how really it can be obtained? So the next part is how. It again includes two interrogative sign actually. The answer initially it looks like that, how? Using the proper operator. Using the proper operator. So you have to again understand what is the operator. So far, suppose we don't know what an operator is, and using how using this operator and the wave function. So this is the question. It continues from the first postulate, because the first postulate claims that it completely describes the system. So naturally the questions we are raising, that how sir and why sir we are saying so. The answer actually includes the answer of two questions, that you have to understand what the operator, and then how we are using this operator to get this complete description, and that answers actually constitute the other two postulates. So continuously I am gradually pushing you from postulate 1 to postulate 2 and 3, or 3 and 4 maybe. Okay, so to understand what a proper operator is and how probably we can use that operator. So like in thermodynamics, we get first the first law of thermodynamics, and then we raise some questions which are not answerable from first law. Then we push towards the second law, and then again push towards the third law, and so on. So here again, the first postulates is explaining a lot, but it raises some questions, and you are pushing forward towards the next postulate. So postulate 2. So would you please read it out on behalf of me, someone of you?
Sir, will I read?
Your name please.
Sir, my name is Bolumi.
Okay, go on.
For every measurable property of a system, such as position, momentum, and energy, there exists a corresponding operator in quantum mechanics. An experiment in the laboratory to measure a value for such an observable is simulated in quantum mechanics by operating on the wave function of the system with the corresponding operator.
Yeah, the next one.
To every observable in classical mechanics, there corresponds a linear operator in quantum mechanics.
Thank you. So the next one is a smaller one. So let me read it out again. Postulate 2 is simply, it says that to every observable in classical mechanics, there corresponds a linear operator in quantum mechanics. So that is the definition, how it is defining an operator. It is not really giving the operator form, but it is saying, it is giving you the foundation of what operator is. It tells that for any observable, there is an operator. Okay, there is the postulate that for any observable there is an operator. I ended the first postulate discussion with that line, that how it is a complete description. I told that it is a complete description because it can give you the any other observable by using some operator and suitably using it. So the part of the question is answered here, that operator is there for any observable. And then we'll follow gradually answer the next question, that how really we are using this operator. But let us in the meantime see what it really means. Postulate 2, that there is an operator, moreover it is a linear operator for any observable. So let us go ahead. So the thing is that how you can really get an operator in quantum mechanical form. When we already have a classical property, say position, say momentum, say energy, say whatever it is. So we have a classical property, suppose A is the name of the property. Then a quantum mechanics postulate says that there must be some quantum mechanical operator of that A, and we call it A cap, right? But till now we have not explained that how really to get that A cap from A. What we have at our hand, we have the classical expression of that A, classical expression. Say for example, position is simply x, momentum we know, say kinetic energy half mv square or p square by 2m. So we have at our hand the classical expression of any observable A, and it is in terms of position and momentum. If you see closely, you will see that any classical observable, its expression can be expressed in terms of x and px in one dimension, of course, position and momentum. So that means if you know the position and momentum of a particle at a given time, you know actually everything about that system classically, right? X and px. So the main question, how you can transform the classical A to A cap, the answers are two steps. First step, you just write down the classical expression of A as a function of x and px. That we know for every classical observable. Okay. Say for example, kinetic energy is p square by 2m. So px square by 2m in one dimension. And the second step, it is saying that after getting the classical expression, wherever you get x in that expression, you replace that x by x cap, and that x cap is nothing but x dot multiplication by x. So you get a classical expression, you have some x or x square or square root of x or x cube, whatever is there in the expression, you just replace x wherever you get, you by x cap, and that is nothing but x dot. That means actually you are replacing nothing new, x is replaced by x simply. But what happens in case of momentum? In that same classical expression, wherever you see the px, you replace px by px cap operator. But what is that px cap? It is h bar by I del x or minus IH bar del x. So this is the first time we are seeing that it is giving a form, an expression for px cap, right? Of course, the question remains that why so, that I will not discuss today, that how people came to know that momentum operators would be like this, right? Actually, in none of the textbooks it is written, unless it is a very advanced level quantum textbook, and I suppose that none of the teachers in graduation level, they explain that why px is like this. But everyone knows, all on a sudden in the fine morning in the class on the board, they start with writing px cap is this, and then do a lot many things with using this thing. But probably you yourself have never asked this question, neither the teacher have explained that why h bar by I del x is the momentum operator. But now we are happy enough at this point that okay, the postulate is saying like this. Okay, let us be satisfied with that much. That postulate, it is a postulate. I don't know why, because it is not provable, but it is testable. So later on, if I get some time, some coming days, I can prove it, not prove it, I can explain or demonstrate that why logically with reasoning px is like this. Actually, this is something advanced, and I have I have a separate lecture on that. I have never given it somewhere. Probably I will give it to someone or some of you some other day. The name of that lecture is Imagine Yourself as Schrodinger. My title is Imagine Yourself as Schrodinger, and then I explained that supposing you are Schrodinger, then how you are going ahead with your formulas and concepts, and finally arriving at the logical concept that why px should be like this. So that answers the question, but now we are not answering this question. So this is, I'm explaining only that how by step 1 and step 2 you can really convert a classical A into an operator A, where it is the demand of postulate 2 that there is an operator for every classical observable. Okay. So here I've just given example that suppose Vx is some function, potential function. Classically, suppose it is the SHO, simple harmonic oscillator potential, half kx square. So now you are interested to get the operator form of V, that is V cap. So what is my step 1? You write down the formula, classical formula, that is half kx square, and then my step 2 is whenever you see x, you replace by x cap. So you have replaced by x cap, so half kx x cap square, and then you are applying that what really postulate 2 tells, that x cap is nothing but x dot. So you just in the next line you put half k x dot square. So you see half kx square remains half kx square. So that is very trivial, but it is not as trivial in case of px, because px, as you know, it is not a multiplicative operator like position operator x dot, but it is a differential operator because it involves a differentiation del x, okay, for one dimension, of course. So let us see that to note that operator operates on psi from the left. That means some a cap psi. It is not the other way, that psi a cap. You are not just multiplying psi and a cap. It has no meaning. But a cap psi means neither it's a multiplication of a cap and psi, but it is something that a cap is operating on the function from left and giving you some result. And another point, that so left to right is important. That's why order of operation is important. Suppose you have taken two operators a and b, or x and px, then the order xpx and the order pxx, they may not give you the same result, because order is important here. That also you know a lot. It has a name. This property has a name. Do you know? Can you give me the name, associated name in connection with this concept, that the operation is orders is important? Can you give? There is a name of this property, a pair of property.
Muting.
Commutation.
Commute kara. Good, very good. Commutation. So that we have given a name to this, that xpx and pxx, when they are same, that is ab and ba, when they are same, then ab minus ba is 0, and then we call that a and b are commuting with each other, and the term ab minus ba, the whole term is called the commutator. So when the commutator is 0, then we call they are commuting. And in simple notation we write third bracket a comma b, third bracket closed. This is the notation for commutator, and when the value is 0, then they are commuting. Well, that is about the name and definition, but can you give a few more words on its significance on this commutation property? Anyone please? How is it significant?
স্যার কমিউট করলে আনসার্টেনিটি প্রিন্সিপাল ফলো করবে এরকম কিছু?
Good, এরকম কিছুই ঠিক. Thank you. So that is even more important. So that we will discuss later on. So you are right. It is connected to the uncertainty. And one more thing, in the McQuarrie form, that operator is linear. You know, it is mentioned that it has to be not only operator but linear operator. So my question here, that in fact all quantum mechanical operator are linear. Not only linear, later on we will find that it is also Hermitian. So I am leaving it with questions. As far as linearity is concerned, first of all, what do you mean by linear operator or linearity? And secondly, why is it needed? What is its significance? Similarly, it demands that all the quantum mechanical operators have to be Hermitian. So the question follows, what do you mean by Hermitian operator and why it is needed? So that also I suppose that you know, but I am just putting these questions in the right place only. So that is about, and here are a few examples of expression. You know, this is the symbol of the this is the name of the property, right? Position, momentum, energy, and then usually how do you symbolize them? This is the simple symbol, and we need an operator form. So you just see a cap is put on head, টুপি পরি দেওয়া হলো, so they are the symbol of the operator, but actually what they are, this is the form. So it is multiplication by r, the px is the differential operator, and so on. Px and this p is actually the three-dimensional p, Tx is one dimensional and T is three dimensional. As I have already mentioned this thing, and this is called del squared, del hyphen squared, del squared, or Laplacian. Okay. Another set of operator like this, potential energy, total energy, angular momentum. So these are the few, very few important for you only, for your purpose only. So these are the a few operators. Okay. So I think you are a bit tired. So should I stop here? Next day we can discuss the other three postulates. I suppose that if you suggest me so.
একটা আছে প্রবাবিলিটি ডেনসিটি, একটু ওটার মধ্যে ডিফারেন্স একটু বলবেন আরেকবার?
Okay.
Probability
Okay.
and the difference between probability and probability density.
Okay. What is mass density, or usually what you know as density actually is mass density? What is the definition? Rho of mass density, mass by volume. So mass density is mass by volume. If it is so, then is it that mass and mass density are same? No.
No.
Mass density is mass divided by volume. Similarly, probability density is probability by volume. Clear? First point. Second point, in case of the earlier one, from density is equal to mass by volume, how do you get it back? Mass by multiplying density, cross multiplication, rho into volume, that gives you mass. Similarly here, probability by volume is probability density, so probability you get it back by multiplying probability density by volume. It's as simple as that. Is it clear now?
Okay, sir.
Okay.
হ্যাঁ স্যার।
Okay. Any other question?
ওই অ্যাক্সিওম, পস্টুলেট এবং থিওরেম, এই জিনিসটার যে ডিফারেন্স হয়, খুব ছোট ছোট ডিফারেন্স হয় কিংবা যাই হোক বড়ই ডিফারেন্স হয়, ওটা একটু ইলাবোরেট করে বলবেন?
আচ্ছা, ওকে।